You can go ahead.
Okay, so thank you very much for the introduction. Thank you for coming. So yes, Edgar Javer, Edgar Java, depending on how you want to, depending where you come from, actually. Today I'm going to talk about. So the title is become clear right after the. I'll give say more the backdrop to all of this work, but to give maybe a bit more context to what Hara just said. So I defended my PhD. I did a PhD in collaboration with EDF, which is Électricité de France, which is a utility company in France, and so it was an industrial PhD. Basically, we tried to do applied mathematics for their problems, things involving uncertainty quantification for prognostics. And so right now, yes, I'm at ENS Paris-Saclay working still on UQ topics, and so this is mostly the work that was at the end of my PhD. I won't talk about the application until the results section, but so yeah, I mean, you can jump if you really have some questions, or we'll keep it for the end. I'll be very broad by talking about complex engineering systems. So what I put in this is a very broad category. Okay, I try to make I come more from this side where you go energy producing assets and more exactly like nuclear reactors. But of course, in this team, I work involving wind farms or things involving bridges, trains, or infrastructure. You could think about dams. And what is the problem with all of these complex engineering systems is that once that they're built, well, you have some sort of loads that are applied to it during operation. This can mostly be mechanical loads. And over time, the problem with these loads is that they create degradation patterns. And these degradation, I'll call them delta T for now. So it's a degradation rate at time T, so say present time T. And so the question is, okay, so we know these systems are operating, they're degrading because that's just how nature is. And during this operation, we might want to monitor, for instance. And for monitoring, we could acquire some data, putting some nice sensors here and there, and perhaps building data-driven models to assess, to diagnose what is the degradation state. And normally, or depending on the system, we could think about perhaps doing maintenance or actual replacement. And for maintenance planning or replacement planning, in that case, what we truly need is prognostics. And prognostics, well, that's where it becomes a little bit more critical when we come to data acquisition, because we cannot really know how the degradation pattern will be on a specific system in the future. So that's where often we can say, even though in some cases this is not true, but data-driven models may not be enough. And so that's where we come to something new. I mean, something that's quite old in the history of science called physical modeling. And modeling of degradation, well, today we can enhance this modeling by using the data. And so this is more or less the framework on which I'll build this presentation, when we were interested in sort of maintenance planning, so basically doing prognostics of degradation rates for engineering complex systems under loads, and where we have some sort of data and where we have some sort of physical models. Okay, and this is quite classic. Well, we've heard about this already before. It's probably data assimilation that we got to do. But what are the challenges that I'm going to address more specifically in this case? Because there's tons of literature on these topics. For what comes about physical modeling, I'll really be interested also in the uncertainty aspect of the physical models. So especially epistemic uncertainty, perhaps model form uncertainty, and the fact that it's a costly computational code. And with the data, that's where it's also in the title of the presentation, and talk about what we do in case the data is sparse in time and perhaps in space, and where you have heterogeneous sources. So for instance, you have different operators or different sensors that give us some measure that may be related to degradation. Okay, now this was a sort of an illustrative point of view. Now to become more mathematical, what would we talk about this degradation index, delta T, is what we're interested in is, so if this is just a scalar quantity, we want to evaluate the remaining useful life for a fixed threshold, delta star, which can be fixed depending on operation considerations, on cost considerations. It really depends on the industry, on the system. Um, and we want to evaluate what is basically the first time at which the degradation rate will be above that fixed threshold. And this is this remaining useful life is the quantity of interest in this presentation. So this is what we evaluate when we try to do prognostics. And so, as I said, well, we could use physics-based simulation codes and data-driven methods, but what we're going to try to do is, for instance, do a hybrid framework. So forget the SG clogging that will come later, but build a hybrid framework in which we combine these two aspects of physics-based and data-driven methods for prognostics. So that could resemble data assimilation, but it's not straightforward. And you'll see why. So now I'm going to fix some notations. I'm sorry for this slide. It's a lot of notations, but this is more mathematically what I've been talking all along. So the type of physics-based model that I'm interested in is a computer code that outputs a trajectory. Okay, so a full trajectory gives us the points in time. Of course, now I'm looking at scalar quantities in time. It can be a field quantity that doesn't really matter. But what's important is that for one given set of input parameters, we get a full trajectory, and those parameters do not evolve in time. So already we see here there's a slight shift from the original point of view in data assimilation, where uncertainty is not modeled by it doesn't evolve over time, but it's really modeled internally like sort of a latent variable that then propagates over the whole trajectories. And we know a little bit of physics about this, but I'm still gonna consider it almost like a black box. So we're not going to do any intrusive stuff on the model, but we will assume that we have a couple of or one surrogate modeling strategy will give us sort of fast evaluations of this code. So that's what I'm going to call the node G hat. And so this is the physics side, and on the data side, we'll talk about what are these data groups. That's the way I named them. And we have to imagine we have heterogeneous groups in the sense that calligraphic D here is the vector of Q sources, and these Q sources, each one has a different size, meaning that we have MI is the size of one vector, and they're all, of course, related to we assume they're related to the true degradation state up to a normal noise with no variance. And what is the difference, and why are they heterogeneous? It is because we assume that the variance is basically different between the groups, but they're the same inside the group. And so, okay, that still can be treated sequentially using data assimilation, but this is maybe not entirely interesting, but it's relevant for what I'm going to explain later. But the true divergence from the original methods comes from the way we define a physics model. Okay? All right, so that's why I love this sort of offline data assimilation, because we're not going to really properly work online. We're going to work with the whole trajectories given as a whole. But we imagine, in fact, that we have a computer code that can output the whole degradation trajectory. So we can extract some quantity of interest that gives us the degradation rate over the entire lifespan of or the entire simulation time of the asset. And the idea is we're going to do sort of like offline sequential data assimilation using surrogates. And now if we denote, so in data assimilation, so like the Z here, which is the state variable, where I'm going to put inside the input variables of my computer code and also the surrogate output. And as you can see, the surrogate is in fact not exactly the code, it's like a perturbation of the code. It's important here to know that we're not really looking at the exact code. And the inputs are not evolving, so there are uncertain parameters, but they do not evolve over time. And so the goal of data assimilation in general, it is okay, given a set of data, it is to evaluate this posterior distribution, P of the state condition on the data. And this we do it using Kalman filters, for instance, or you name it, particle filters. But when we do this, we do it sequentially. Okay, so we do it at a time step, and then we update, we propagate first, then we update, we repropagate, and we do like this sequentially. Here, this is not the right framework because everything is sparse in time. So we don't have a arrival of data, continuous arrival of data. And also the code has these uncertainties that are propagating over the whole trajectory and not sequentially. And so how we're going to do this assimilation, so evaluating the posterior, we'll do it by sort of a modular approach. And this modular approach involves first treating, I mean, it means separating the two. So we're going to first like treat the uncertain variables, the input variables. So we're just going to do sort of like a Bayesian model updating, a way to evaluate the posterior. And then we're going to apply smoothing on trajectories of the surrogate. And this smoothing really is going to be like the more like ensemble method. And at the end, we can more or less get the approximated posterior of the state variable by basically, you see, separating the two independently, the first and the second study. Okay, now more in a picture to again give us an illustration of what we're trying to do. So as I said, the ingredients are, so we have a computer code that gives us some sort of trajectories, full trajectories over time. We got data groups, heterogeneous, meaning with different variants, and sparse in time, and that's it. And I add here, okay, an additional quantity, which is maybe not entirely relevant, but still, because one may wonder, okay, well, we said that we had like degradation data in the past, and you want to use it somehow. Maybe you're not interested in only performing prognostics, but you also want to know, for instance, if your code more or less follows the data patterns as you've seen before. And so that's why for instance, we could look at the whole trajectory as a set of, maybe we can separate them as a set of window frames to be even more general, in which, for instance, we can separate the different scenarios in which the DS has gone through. It can be seasonality, it could be whatever. And well, the all that we're interested in is this prognostics frame. But still, we want to maybe calibrate the trajectories before. So as I said, so we start with this design of experiments, then we perform this, so we separate the Bayesian model updating and the ensemble smoothing. And if we are on the last frame here, on the prognostics, then we evaluate the remaining useful life. And I haven't mentioned it, but also on those engineering systems and subject to loads, etc. Well, the problem is if we just use one method that gives us perhaps 1 point value for the remaining useful life and no risk involved. Of course, take for instance nuclear industry. This is a bit problematic. So we want to know margins, and we want to know so basically like or how it behaves maybe in the tail. So we're really interested in the probability distribution. So that's why I call here a remaining useful life distribution as just a point value. And once we have this, then an operator or an engineer can base a decision of maintenance or replacement and go on. Okay. And about this probabilistic aspect of rules, so maybe you've seen papers in which the remaining useful life is again evaluated using some parametric, or like we put some prior on the remaining useful life and then sort of update it and imagine it's a Gaussian distribution, and then we just update it. Here, the strength of this method is that again we can compute it in a non-parametric way. We just use Monte Carlo samples to evaluate the distribution, and we just with the kernel method we can get the full distribution. So this is another strength of getting a non-parametric rule from once we've performed all of those steps that I mentioned. Yeah, these formulas are ugly, but so what does it say? It says that, okay, if we look at the cumulative distribution, we condition the remaining useful life to a certain threshold over the data. I mean, this is just I mean, probability formula that gives us. We're looking at the posterior distribution after conditioning on the data and on the inputs, and on the projection. Okay, yeah, the projection. What? Yeah, this is getting into maybe too much mathematical sophistication. Perhaps we can talk about it after. But That's why the J and Q. And okay, so now I've said there are two steps. So we have the the Bayesian like model updating and the ensemble methods or like the smoothing method at the end. And so for the first step, we're gonna we're gonna like what we've put in place is a sort of an algorithm that is divided in 5 steps that works that more or less has its advantages to work in most of the cases because we really use basic stuff in here. So if we describe it in a nutshell, we look at the input. So we're interested in the distribution of the inputs conditioned on the data. This is the Bayesian model updating step. And to evaluate this distribution, we're going to look at our vector of inputs. And we're going to select one input at each step, which we find more relevant in terms of its influence on the data. Okay. So, okay, we have our design of experiments, we have our set of trajectories, we've just propagated a uniform prior on our we've propagated our uniform prior on our inputs on the code. And so we get a simple design of experiments by we just sample uniformly on those inputs that are considered independent, no problem. And after that, we compute something called Hilbert-Schmidt independence criterion indices, which are sort of a sensitivity analysis indices, maybe that you know, maybe they're more familiar to machine learning people. So why are they interesting? It is that they provide sort of similar results to what we get, for instance, using Sobol, but with a much lower price because we just need a sample, a data sample. We don't need surrogates, and it's not very expensive to evaluate. If we just have, for instance, 100 data points, we already can evaluate. We have estimators that perform very good to get to perform like ranking on the variables. So that's why we use HSIC here, and we look at it at. That's why I was saying that it's the influence of certain marginals on the data instances because we look at the ranking averaged over the time instances of the different data groups. And so basically, we're looking at which variable is most influenced on the points in the model that have the data. And so after ranking this, we select the one that has the most. It works like a solo. We set the input variable to update, and I denote the theta k here. And then we perform a surrogate model. And here is because we assume that our code is very time costly, and we want to then afterwards do some MCMC, though we need a lot of evaluations, and that means we need to we need fast evaluations of our code, and so we're going to do some sort of surrogate model. Now, the problem is immediately when we use a surrogate in these sort of approaches, we're not using the original code, then we're inducing in the Bayesian formula some sort of conditioning on the hyperparameters or on the certain surrogate that we're choosing. And so how can we integrate this sort of model form uncertainty or perhaps more sort of like a bias of meta modeling is to not build one, but build maybe P surrogate models and sort of aggregate them using a convex aggregation and use this as a surrogate model instead of just one. Okay. So because we have set the input variable, so after the ranking step HSIC, we have set one input variable, and then we set up the other d-1 variables, and then we just fix them at a nominal value. And that green U0k, so the k is the iteration number. And this is still like a question of, because we're working just marginal by marginal, but this is like a no pre-lunch theorem because we're still sort of conditioning on these latent variables. And so it's still a question on how we can integrate them. But maybe just to say a word about how we do the surrogates here. we're just gonna do like a sort of non-intrusive reduced order modeling scheme, but maybe you already know all of this, so I'm just not gonna go into too many details. I call it Faraday law of expansion because here we use we look at parametric reduced order models, and the only important thing here is that we use a Gaussian process to learn the models. And so what will be the difference in terms of surrogates here will be that, for instance, we use different prior, mean, and kernel in order to learn different terms. But now, assuming that they're all behaving more or less the same on some validation metrics, that's why also I mean, imagine you have two surrogates that are constructed differently, but like really more or less like give you an R2 like a regression score of 0.99. But it's okay, now how I'm going to select one or the other? You know you're going to induce some bias, so that's why we just aggregate the two. And this is the combination of aggregation scheme I was mentioning, which is just like getting a convex aggregate of the p circuits. And so this gives us some sort of bias minimizing at the price that we pay, that we're giving sort of some new hyperparameters here by putting in weights. Okay, so the fourth step is estimating the proper posterior. So that's why MCMC works simply here, no need for Hamiltonian Monte Carlo sampling or anything, because we're just working with one variable. So this is what the advantage is. We know that, okay, this method works. And of course, the question can be asked, but then why didn't you like work with groups? And you only work with one parameter. Why didn't you just calibrate the whole input distributions at once? Without saying that, perhaps you may have some issues in the MCMC approach, and you want to create a generic method. Also, the thing is here that HSIG I was mentioning really works with one input. So the ranking doesn't work with groups of inputs; just works with one input, and so that's also a reason why we did this. Of course, we can further discuss later if you want. But the idea is for the MCMC step, we get the estimated posterior for the selected input variable using MCMC, like the most basic random walk metropolis hastings. And so our more or less our cost function will be to evaluate the information gain between the prior and the posterior. And what we do in the case where, so we compute the Kullback library divergence here, it isn't entirely it is sort of an information metric. Of course, it has its flaws because it's not really entirely a distance, but it is an information metric. And so on computing between the uniform prior and the estimated density, and knowing if we, for instance, here we have a set of tolerance of epsilon, so imagining that this is greater than epsilon, then we just replace the kth marginal with this updated distribution and repeat. So that gives us, again, a new ranking where we have a new update variable and we have a new surrogate. So basically, we also refine our surrogates at each time step, at each iteration. Okay, so if you're into Bayesian modeling, you might ask, okay, so what the likelihood model and what price did you put here on your data on? So this is a certain. This is where the heterogeneous sort of the assumption on the variance comes in, where it works well because basically we get this this nice formula 13 here for Q different groups that have different, where it's just our marginal distribution will be the product of distances between the code and the data. But at a power of the number of data points. And this is a simple generalization of a previous result. Got from a paper that works more on Bayesian calibration, where they use a gamma prior distribution on certain gamma priors, you can see, on a certain transformation of the variance. And why we do here? Because, well, we are integrating the variance of the noise in the. Okay, but this is too technical, not important. At the end, so our our posterior will look something like this. And as I said, we just use a simple MCMC That works pretty well because we're just using in one dimension. And we also integrate the induced uncertainty basically on the choice of the convex aggregation parameter. We integrate it by just sampling with a Dirichlet distribution on the simplex and that gives us a Monte Carlo integration of the hyperparameter. And we test the convergence using Gelman-Rubin tests. And the problem is, again, no free lunch, you got the conditioning on the latent variables. And that's a question on perhaps how we can integrate this additional uncertainty. It's always like this in Bayesian statistics. You thought you solved a problem, you got a new one, and you sort of create new problems by solving others. That's just mathematics, how it works. Uh, iteratively like this. Okay, but this using some numerical tricks, we can sample efficiently in this posterior. Okay, brutal transition. We got a slide here. Well, okay, so after this BMU step, we got to the point where we've updated our marginals, and now we repropagate with our last surrogate the uncertainties. And the question is, okay, can we stop here? Well, if we look back at the original setting of data assimilation, we still need that trajectory updating step. And for that, well, this is where ensemble methods can be used because, this is, if we look at filtering, the filtering would want to update something like this, where we want to get the posterior on the last time step TK condition on the data, right? Now the problem is the data is unavailable at each time. So if you look at the data assimilation mechanism, again, you propagate and you update, and then you repropagate, etc. But when we propagate, we have no data. We just remain with the uncertainty, and we cannot reduce it. And so when we repropagate, doesn't make sense. So that's why a better way to handle this is by using smoothing, where here we don't look at the last time step, but in fact we look at the whole time frame with up to TK, and we smooth it over the data. And so this is it bears exactly the same name as the ensemble Kalman filter, but you can look at it exactly as a ensemble Kalman filter with the difference that, well, here your state variable has dimension k. Just a vue de l'esprit. And so for this is just basic Kalman formulas. So we propagate our last posterior. Sorry for the typo here. That's not H but a P, and it's a G hat. And for each data group, so we can compute the data, the ensemble means, and the anomalies, and then we compute our cross covariances between the time where we have the observation times of the data and that of the code. We get a cross covariance matrix, and then we define the Kalman gain, and then we update all the ensembles using the common formula here, using the innovation term. And not unsurprisingly, we still get sort of like a sequential, like an online step, but the thing is here that we work observation by observation. So just to give you maybe I should do an animation for this at one point, but you got your full set of trajectories. Then imagine you have one point here in time, and then you reduce a little bit all the trajectories. Then another point you reduce, and then another point you reduce further. So still, it is like an online method, but you work with the full trajectories. So it still works sequentially in a way. So that's why the formulas are essentially the same. Okay, so after this 30 minutes of mathematical grounding, it's time to talk about application. And so that's where we come back to, say, my original problem. So the problem of my thesis was to work with certain components in nuclear reactors. Okay, so in a nutshell, so there are different technologies of nuclear reactors. This is the one that's most used in France. It's called the pressurized water reactor, and it consists of three hydraulic circuits, and the three hydraulic circuits interact with what we call heat exchangers. So the primary circuit is the one in yellow here. That's the one in which you have the reactor vessel, and that's where you get the nuclear reaction happening, and so that water is heated up. and then the heat is transferred to the secondary circuit in a system called a steam generator. So as the name says, it's like a huge boiling kettle. But what you have, in fact, it's not like a joule energy that's transmitted, but actually just heat from a primary circuit in some tubes that is transferred to a secondary. Um, and so the secondary one, basically, the liquid just evaporates. And the problem is that over time, inside these, sorry, I'm highlighted here. This is the component I'm talking about. Well, you have tubes inside that basically get clogged. So this is how it looks before and after. And this is the sort of load I was talking about. It's a complex operating system with loads and, of course, sparse data because we cannot access it. You see, the steam generator is inside a building, which is separated from a second one. And so inside this building is called the reactor building. You cannot enter while the reactor operates. So basically, also there are sensors, but related to different stuff, but definitely not for clogging. And so the only way you can measure data here is by stopping the system and putting in cameras. And again, you're not going to see because that system is like 10 meters tall, and you cannot see what's inside. You only see like what's on top. Many issues. But at the same time, the problem exists, and for like old reactors, we have to address this somehow. And what they do is they perform chemical cleanings. And so basically they've asked R&D department, can you help us with finding a way to get better maintenance planning on chemical cleanings for flogging of steam generators than just taking the last data point and drawing a straight line with a ruler. Okay, so this is the topic. It's not very important. So, okay, yeah, this is more related to my PhD. The question is, you haven't got a lot of literature, but and the data is sparse both in time and in space. They're heterogeneous, and the question is how to make use of all this available knowledge, like computer code, which has exactly the same behavior as I've explained, the data groups, and the lack of trustworthy tools. That's why we're doing sort of hybrid methods, and you want to do prognostics, and you have to base a decision, and you also want to build a digital twin. Right? You want to do a lot of things with a lot of tools. We can always try and build something out of this. And so the computer code is called the tick buffer depot, not very important, but it's a complex multi-physics code, and that's why also you can see why we didn't do like intrusive surrogate modeling, because here it is a complex chaining of three codes that, well, it's very complex to handle. It also takes a lot of time to compute just for one input, set of input variables. And for a specific system, for a specific steam generator, we get the whole lifespan, the clogging rate. So the degradation here is this clogging rate tau c. We get the whole trajectory. And so these are the input variables. Okay, they look a little bit strange like this, but some of them are so input variables that have uncertainties that are, I mean, here still somehow we needed some experts to give us the supports of the input distributions. They're more or less related to the nominal functioning of the code, but also to some physics modeling, but you still need some expert to help you out with this. And yeah, and this is how the posterior distributions look like. So, okay, these are all the three windows, not important here, but the last one is the one that has the prognostics window that we're interested in. And you can see that on the seven variables, you got 5 out of 7 that got informed by the available data. And also some of them have an interesting behavior because they also behave like they shift modes in between the time windows. This is interesting, well, because the time windows here are related to some sort of scenario chemical conditioning stuff, but this is in the paper if you're interested. And now more specifically, if we look at the trajectories of this were the prior trajectories, those were the data points we had. Those are the time frames, the time windows, and you can see after updating and after smoothing, we basically get a much more reduced uncertainty, that being the goal, okay? Hopefully that we're going to reduce the uncertainty, the prior by conditioning. And you can see the prior trajectories have really been smoothed out. And now if we look at and this is the cherry on the cake, because you get the posterior remaining useful life distribution, which is much more informative. Because if you looked at with all that you had in the prior uncertainties and the data, already you couldn't really build they've tried but not really succeeded in building a data-driven model that could do prognostics because they didn't know how it would behave like in the future. I mean, it's complex. But you have parametric uncertainties on the code. But then, okay, first of all, you do Bayesian model updating, you already shift your uninformative prior rule, and finally, after smoothing, you really get a nice distribution. So this is good, positive impact for maintenance planning. Okay. So take home messages. So thank you for bearing with me on the maths. But the idea was really why I started by explaining the maths is to show you that the method has the feature of being generic. So you don't need much more than like my third slide, I guess, where I give you how the tools look like. So you've got the computer code and the data groups, and then it just works. We also have a toy case on a like crack propagation problem that is also in the paper. And the idea is the goal is to reduce this parametric uncertainty of a simulation code by and getting a better rule distribution to achieve more informed decision making by using the method. And we've demonstrated on a really complex nuclear steam generated use case where we have really substantially reduced the remaining useful life uncertainty. And of course, still works. It has to be done because here we work with just one system, and we could see how it behaves on different systems. But if you want to read more, so the paper is published in Reliability Engineering and System Safety, and there's a GitHub repo in which you can try if you also have problems that look similar to this, and please reach me out and or like try the GitHub repo. Everything is inside. Okay, well, I'll maybe just before ending give a few questions on additional work and some extensions and some future work. So the question is, okay, so we still have that problem. It's like on the maybe mathematical side on integrating the uncertainty and the nominal parameters. And just to give you a flavor of why this just doesn't work with a simple Monte Carlo is basically if you just look at one marginal and say you have d-1 variables, I mean you try to integrate by simple sampling, then automatically just one direction won't move enough in your sampler in your random walk in order to really converge your Markov chains. So you have to find something smarter there. We're looking into maybe like variational autoencoders or stuff like that. But now an additional extension or maybe addition to this work would be, for instance, to use also to address the model form uncertainty I was mentioning, to use conformal prediction for this. And so I've worked on conformal prediction for a certain type of surrogate, so Gaussian process surrogates. And now the important feature though for using conformal, I don't know if you have a lot of experience with it, but what you want to get is having what is called adaptivity, meaning that so okay, yeah, for those who don't know, like conformal prediction gives you not only a point estimate, but gives you like an interval, a prediction interval. And now the problem is on like easy standard types of conformal estimate is you just get the same size for different data points, and that's uninformative. If you want to correlate, for instance, with an approximation error, model form uncertainty. And that means you want to get adaptive intervals, meaning adapting sizes to the new data points. And we've managed to do this for the GP surrogates, and also this is available on GitHub for the trial. And in a specific case that also is useful for industry and cross-conformal because cross-conformal basically uses a smaller data set than you can get using uh, leave one out surrogates. These sort of intervals that got the coverage properly. And the question is, can we use such proxies for meta model accuracy to in some step of the method that I've described before for a surrogate refinement or perhaps for active learning? So this is future work. I'd like to thank you for your attention and let's connect. And yeah, about to take your questions.